Are you leaving tomorrow?
Tomorrow, yeah.
I was gonna,
Yeah.
how are you posting notes?
For your?
Well, in general, I mean,
Yeah.
so I have notes that
on our MagLab website, yes.
I mean, eventually,
yeah,
right?
we will post it.
Okay. Yeah, I have a mediocre copy. The last 2 pages I took pictures of, but
notes have already been sent for printing.
awesome. Yeah, I saw that email.
No,
I just have
will
notes.
Be posted on the website.
Yeah, because
you give it to us, if you want it to be posted.
yeah, I do.
Okay,
I do because they're going to be much more detailed than what I'll manage to write on the board.
Yeah.
Yeah.
Your tutorial notes were also posted, I think.
Mm-hmm. Yeah.
Yeah, so we'll just go by the clock in the back of the room.
Okay.
So we'll start at 5 after, end around 5 after, or whenever you want to wind down.
I'll try to wind down by 6,
yeah,
but
whatever.
we'll see what happens.
We'll keep it going. If people are fading, then we'll just quit.
Yeah, I'm standing between everyone and dinner.
But that's fine.
It's been a long day, but
that's why there's coffee, and that's probably what everyone went to grab. But yeah, I think people are trickling back in. Actually, a lot of people are trickling back in, so this is a good time to get started.
All right, I'll go back.
Yeah. All right.
Sure.
Okay, let's get started. Everyone perk up. It's on. You don't. Our last speaker for today is Rebecca Flint talking about quantum spin liquids.
Okay, so thanks everyone for staying with us till the last talk. I know I'm standing between you and dinner. What I want to do is sort of give an introduction to quantum spin liquids. This is going to be a fairly high-level overview. If you want details, you should go look at some of the good reviews. This review by Lucille Savary in the Valence is particularly good. What I want to do is to give you sort of a hand-wavy overview where I hope you can get some of the physics ideas. So we're going to start from the very basics. So today we're just going to talk about insulating local moment systems, even just focusing on spin 1/2 Heisenberg lattices, where I can write my Hamiltonian like this, and I'll mainly be thinking about 2 dimensions. And what we're interested in are quantum spin liquids, and the first main characteristic about them is that they do not magnetically order. So this expectation of S is 0. So our goal today is to discuss quantum spin liquids generally and very briefly introduce long-range entanglement and topological order. And you can do that on slides. And then we're going to talk about using parton representations and use this to illustrate some of the key ideas in quantum spin liquids. And then for that, I'll move to the blackboard. I understand it's a little difficult to see, and so you'll have to ask me lots of questions. Tomorrow, you're going to do a tutorial that uses a lot of these ideas. And on Thursday, we're going to go back from this very abstract theoretical discussion to connect how we connect to real materials with much more complicated models. All right, so the basic sort of initial idea you need to understand to think about spin liquids is this idea of a valence bond. So this is not a valence bond, but what I'm saying is if I have a spin 1/2 on each sites I and j, the simplest state that I can write down is a kind of product state where I have spin up on side I and spin down on side j. This state is not entangled at all. And what we know, if we have an antiferromagnetic interaction between these sites, is that the ground state will actually be this entangled state that's a spin singlet. And this is simply what we call a valence bond. I'm going to be drawing some pictures. They're all going to look like this. And it just means it has this entangled spin singlet state. And part of what we mean by entangled is that it must be written as a superposition like this. There's no way to rewrite it in a different basis where it's not written as a superposition. And so what we can do when we're starting to try to construct states that don't have any expectation of spin is to just construct states where every single spin is in a valence bond. So as long as we have an even number of states, we should be able to do that. And this is going to be some state where I don't have any magnetic order. And so this idea we can do sort of the simplest thing, and I can just arrange these valence bonds on a lattice. This is an example of a valence bond solid. So you see that my valence bonds themselves have formed this nice order that breaks translation and rotational symmetries. And in fact, this is a state that has a short range entanglement. So these two spins are entangled with one another, but these two spins are not entangled at all. So it's really just nearest neighbor entanglement. And so this is not a spin liquid, but we can go from here to this sort of simple idea that Anderson introduced of a resonating valence bond state. So instead of having a single configuration of valence bonds, I instead have a quantum superposition of many different superpositions. So I have this state, I have this state, I have this state, and I have infinitely many more states if I have an infinite lattice. And so this state, these kind of resonating valence bond state really has a long range entanglement where this spin is actually entangled with this spin because of all of the resonance of these valence bonds. Okay, and we can see a lot of things sort of in a very hand-wavy sense just from this picture. So you get the sense of the long-range entanglement, although it's clearly not very quantitative. And you can see that, sorry, if I take this bond here and I break it, that's going to cost me some energy J. And I get two spin 1/2 excitations. And they're neutral spin 1/2s. And I can move them around just by resonating valence bonds, which costs me no energy. And I can do this again and again. And that lets me move my spin-ons apart. And we call these deconfined. And that gives me fractional excitations. Yes? So, okay, so everything is in a quantum superposition. But one way to think of it is to say that it just, oops, sorry, wrong way. It just goes from here and it like resonates from here to here. So it's just more like it's resonating from this configuration to the previous configuration. I didn't have any things where you're just sort of flipping two spins. That's kind of the basic sense. Does that help? So it's really just a quantum superposition, and you find sort of equally likely quantum superpositions that cost you no energy this way.
One quick question.
Yeah.
So these solid lines indicate that there is interaction between these spins.
Yes, so I have nearest neighbor triangular lattice here. Yes, thank you. Okay. So spin liquids, so long-range entanglement was the first idea I wanted to introduce. Topological order is the second idea, and these are actually very intimately connected. And so here's our valence bond again, written in Bra-Ket notation. And as I said, valence bond solids have short-range entanglement. Resonating valence bonds have long-range entanglement. And we can measure this entanglement by calculating the entanglement entropy. And I put measure in quotes simply because we do this measurement numerically, and we don't yet know how to do it experimentally. So what I'm thinking here is this whole slide is my system. I haven't drawn any of the spins. And I split it up into two regions, A and B. So ignore what's going on the border of A and B at this point. And I know the ground state wave function of my system. So I can use this to calculate the reduced density matrix by tracing out all of the degrees of freedom in B. And then I can use this to calculate the entanglement entropy, which is something that only that depends on basically how I've partitioned my system into two shapes. So this is this trace involving the reduced density matrix. And so we know actually a lot about what entanglement entropy does when we're looking at the ground state of a system. So if I have a product state, like think a classical ferromagnet, this totally vanishes. Otherwise, it takes this form where I have some term that's linear in sort of the perimeter length here. It's often called the area law because we're thinking in three-dimensional systems. I have another term that doesn't depend on this, and then all of the other higher order terms vanish once I take the length of this boundary to infinity. So this first term is called the area law. It's non-universal, which means it depends both on the details of what your boundary looks like and on the details of what particular region of the phase you might be in. However, the second term is really interesting. This is the topological entanglement entropy, and this is universal. So if you can calculate it correctly, you will always get the same answer no matter how you do your boundaries and no matter where you are in one particular phase. And so for trivial phases like magnets or valence bond solids, this is 0. For spin liquids, this is non-zero generically. And it's quantized, and so for 2 particular kinds of spin liquids that we'll talk about later, this takes the value of log 2. Okay, and this is something that we can really concretely access in some kind of numerical simulations. Yes? Yes. That's going to depend on the particular type of superposition. Yeah, so that's actually, the first caveat is this does only work for gap states. We can really only define topological order sharply for gap states at this point. And so if you have a gapped state, you can uniquely define these topological invariants, and you can have this kind of strict comparison. Now, there are also gapless spin liquids, which are really interesting, and sort of characterizing, classifying those is still an open problem. Okay, so the next thing I want to talk about very briefly is just sort of what is possible to have. So I think this is a very sort of abstract theoretical result. It's the Liebschulte-Mattis theorem, which has then been extended by Oshikawa and Hastings. And so what it tells you is that if you have a local SU2 invariant Hamiltonian with a total half-integer spin per unit cell in periodic boundary conditions, the system must have at least one low-lying state whose energy scales to 0 in the thermodynamic limit. So now I want to switch to the board, because otherwise I'm going to talk way too fast. So what I want to talk about is, once we have this, what can we actually get with this, right? So what does this tell us? So I think, can someone help me move this board, actually? I think I don't want to, actually, it seems to be okay. All right, perfect, thank you. All right, so I've blocked the theorem, but, whoops. Can you turn off the, thank you. All right, so what can we get? All right, so one possibility is that we can break symmetry. And in this case, once we've broken symmetry, once we go to the thermodynamic limit, we're going to have degenerate ground states. So that satisfies this theorem, right? So we can get magnetic orders, and we can get valence bond solid states, and both of those cases will have at least 2 degenerate states, and so they satisfy this Liebschulte-Mattis theorem. And so what we're interested is, what can you get if you don't have symmetry breaking? There's also symmetry breaking spin liquids that we're not talking about at this point. So essentially, what we're saying, what the sort of old definition for spin liquids was, is that spin liquids don't break any symmetries. When I was a graduate student, that's sort of how I learned what a spin liquid was. And what it turns out is that is certainly not a necessary condition. And what this Liebschulte-Mattis theorem tells you is that it can be a sufficient condition. And so that's, I think, why this is interesting. So, and just so you know, the better definition is this idea of long-range entanglement. Okay, so if we have no symmetry breaking, we have basically 2 options. We have an energy gap. And so this is the case where we could measure that topological entanglement entropy. And if we have an energy gap, that means there's sort of no low-lying energy states, and so we have to actually have degenerate ground states again, but now they can't be protected by symmetry. So they have to be protected by something else. And so that something else is topology, and so these degenerate ground states are protected by topology. The other possibility is that you don't have an energy gap. in which case the theorem is also still satisfied automatically. So you can have a gapless spin liquid in this case. And this case is still really interesting because you have a gapless mode that's being protected by something, right? So it's not topology in sort of the sense that we can define it when we have an energy gap, but somehow it's protected by the long-range entanglement. Okay. All right, any questions at this point? All right, so what I want to do next is to talk about parton descriptions. So I'll start off over here. So treating spin liquids theoretically is a very difficult problem, both in finding a model that actually has a spin liquid ground state, which is something we'll talk about on Thursday, but also in just solving any particular model. And so what we tend to do is we cobble together lots of different things. So one of the most important techniques that I'm not covering is exact solutions. So usually, so we have a few examples of spin liquids where we can exactly solve the Hamiltonian. They're not necessarily connected to reality, but they give us a really good understanding. So toric code, the Kitaev honeycomb, and other examples fall in here. We also basically always need to rely on numerical techniques. Because we have Hamiltonians that we can't solve exactly analytically, aside from these very few special cases. So we need to go to numerics. And numerics is very difficult, but it gives us a lot of really good results. The third thing is what we're going to talk about now, which is parton descriptions. So this is an analytical result that that essentially tells you what's possible and gives you some understanding of what's possible. So it may not tell you what exactly is going on in any particular lattice, but it gives you a sense of what's out there. Yes? This is too small? Okay. It says exact solutions, numerical techniques, and parton descriptions, and I will be larger. Is that size okay? Okay, thank you. All right, so essentially what we're going to do here is a kind of mean field theory. And we're going to take our Hamiltonian and have something like this Heisenberg Hamiltonian sit on some kind of frustrated lattice. So here I put a single kind of bond, so imagine something like the Kagame. You can generalize this to, say, the J1, J2 honeycomb model that Colin was just talking about. The main point is that I have SU2 invariant Hamiltonian, and I'm thinking spin 1/2. Okay, so when I look at this Hamiltonian as a theorist, I really want to do quantum field theory on it. I would really love to write down some Feynman diagrams or something like that, and this is really difficult to do with spins. You can't do Feynman diagrams, you don't have Wick's theorem, so what you want to do instead is cheat and turn your spins into something that you know how to work with, right? So this is the idea of parton mean field theory, which what you want to do is represent your spins in terms of something else. So we're going to concretely talk about representing them in terms of complex fermions. You can equally well do this with bosons or Majorana fermions. These representations are by no means unique. All you need to do is construct something that satisfies your spin commutation relations. So we're going to construct the simplest case, which is the fermionic representation. And I'm not going to show you the details You can either check it on your own or look at some of the reviews I mentioned. But I can take SI and write it in terms of some pseudo fermions. So here I'm using Einstein summation. These are Pauli matrices. These are some kind of slave particles, pseudo fermions, auxiliary fermions, call them whatever you want. Partons is the sort of more modern term, but they've been called many things over the years. And alpha is ranging from basically up and down. So these sort of auxiliary fermions I can think of as spin 1/2 particles. They're not real spin 1/2 particles, but they turn out to be sort of real enough that we can learn a lot from them. So if you take this, you see I have Pauli matrices there. If you check your spin commutation relations, you'll see that this fully satisfies your spin commutation relations. The one thing you worry about is that we have a fixed length of spin on our site. So I have spin 1/2, so the total length of my vector has to be fixed. Whereas if I just put free fermions on a lattice, I can have 0, 1, or 2 fermions on any given site. So I need to eliminate 2 of these cases. So I get this representation, but I have to use this constraint. All right. Sorry, again? These are fermions, yes. Okay. So, right, they're fermions. I have basically one species of up and down. All right. So, once I plug this in to my Hamiltonian over there, you'll see the resulting Hamiltonian is going to be quartic in the fermions. So I really haven't done too much to help myself out at this point. But I now have this quartic Hamiltonian, and I have this constraint, and at this point, everything is exact, but not very useful. So in order to make things useful, I need to go beyond exact. But at this point, I could have done this with my bosons, with my Majorana fermions. Everything is exactly the same. Now what I'm going to do is proceed by starting to make some kind of mean field decoupling. There's different ways you can try to justify different mean fields. If you're interested in that, you can talk to me afterwards. But right now, I'm just going to say, well, let me write down everything that's possible. So mean fields, of course, are going to be 2 fermion terms. So I can have on-site terms. These will look like this, essentially, due to my constraint. And then I can have terms between the sites, which can either look like hopping terms or pairing terms. And this is essentially everything that I can write down. And now I have to say, well, what am I actually looking for? I want to find a way to describe spin liquids. So spin liquids have to be SU2 invariant. So I can eliminate everything that breaks SU2 symmetry. So my on-site term is totally gone, and these 2 terms get restricted. To these 2 terms here. Again, I'm using Einstein summation. I was not over here. And this alpha tilde is the sign of alpha. So is this visible to everyone? OK. So one of these terms looks like a hopping term, an expectation of a hopping value. So this is a spin coherent hopping. Should I not write this low on the board? No one's saying anything. So I'm going to continue to write this low on the board. All right. So this looks like a spin coherent hopping. And this looks like a pairing term, right? A singlet pairing. But the key point here is that these are both singlets between my two sites, right? So these are actually both different representations of valence bonds. Oh, that's terrible. Right, so here, these things have to be SU2 singlets. So the only two SU2 singlets that you can write are something like a pair singlet, and this is a sort of spin coherent hopping. So one way you could check this is take an SU2 matrix, transform your F's under it, and you'll see that if you try to do it here where alpha and beta are generic, it will force you to have these. The other way you can think about it is by appealing to sort of high energy ideas. So if you think about SU3, we have two types of particles, which are singlets. We have mesons, which are essentially like a blue and an anti-blue, and we have baryons, which involve all three colors. If you get onto SU2, you also get essentially mesons and baryons, but your baryons involve two particles. So these are like your mesons, these are like your baryons. Okay, and if you think about it, maybe you can also just sort of see that these satisfy this. At any rate, these are so these are both different representations of valence bonds. Okay, and one of them looks like hopping and one of them looks like superconductivity, but don't forget that these are not real fermions. All right, so I'm going to call these two different names. I'll write them up here. So between any two sites, I have okay, and I can take these mean fields, plug them into my Hamiltonian, and rewrite my Hamiltonian. And so what I get is okay, so I get a quadratic Hamiltonian in my fermions, where I've written this in Nambu notation, which is just the term for writing in terms of this particular particle hole notation. So here you see the diagonal terms look like hopping, and the off-diagonal terms look like pairing. Is there J missing? Oh, so J went down here. So it depends how exactly you do the mean field transition. So I've totally skipped that. I would look at one of the reviews. It's essentially each of these are going to be proportional. Let's see. So I'm being sloppy. These should be proportional to. These will be proportional to J. So J will be in this magnitude here. Yes? It is a spin singlet between two sites. So the total spin is 0. So that's important.
So, I mean, like, if you flip a spin at, like, site I up from up down to up, and then you can think of at site A as from up to down.
I mean, both of these will do sort of the same thing. Yeah, you have to sort of think about what your background is initially in order to.
It looks like double spin fusion.
I mean, you're going to be creating fermions, but you can only have one fermion per site, so it's all a little bit complicated, I think, and it's a little bit dangerous. Okay. So the one thing, let's see, I do want to go. So here I said we have a constraint that NF equals 0. So we can enforce that constraint by introducing a Lagrange multiplier, lambda at each site. So this is still our constraint. All right. So right now, this looks like some nice fermionic Hamiltonian. And if we forget that these are not real fermions for a little while, let's think about what we can actually get here. So essentially, these partons, these fake fermions can do everything that any kind of normal band structure does. And we're going to call them spin-ons. There are spin 1/2 excitations. We'll motivate that a little bit more later. But so I can construct mean field Hamiltonians that look like whatever I want. They might not be the ground state, even of this particular Hamiltonian that I've written down. But right now, I just want to see sort of what is out there. So just to list the spin-ons, have a dispersion, so I can diagonalize this. So Fourier transform diagonalize. And what I can get from this dispersion is a Fermi surface. So if you just imagine the simplest mean field where I have uniform chi on all of my bonds, this typically gives you a spin-on Fermi surface. I can also get Dirac cones. I can get band insulators. And I can get topological insulators or Chern insulators here as well. Essentially, everything that I can find in some kind of electronic band structure, I can find here. I can also find essentially what looks like superconductivity, but let's be clear and call it superfluidity because these are neutral particles. So this is before we start to worry about what we're missing by just looking at this simplistic picture. So there's a lot of possibilities. The constraint there, I have lambda coming in looking like a chemical potential that's going to keep me fixed at half filling. So this is sort of the first thing that we have to bring us back to reality. So typically, we're going to have our lambdas be uniform, and so we're going to enforce this constraint that we're at half filling for our lattice as a whole, but not for every single site. So we say that the constraint is enforced on average. So this is an assumption that we made in order to actually solve our problem. This can be justified in some large n limits that are nowhere, that are not particularly real, and we can do better by going and enforcing the constraint on every single site. So if I'm just doing a simple mean field theory, I'm only going to enforce the constraint on average, because all I'm going to do is take this Hamiltonian I have mean fields, which are going to be these chi's, these deltas, and these lambdas. I could just solve for them the way you solve for any kind of mean field parameter. And what that's going to do is just give me this case where I'm enforcing the constraint on average. So if I want to enforce it on each site, you can take your mean field wave function. So this will be some kind of Fermi C or some kind of BCS wave function if I have superfluidity. And now I'm going to take this and enforce the constraint at every site by applying a Gutzwiller projector. So this Gutzwiller projector is simply projecting out all of the states that are not a half filling. So it gives me 0, and it's going to be product over all of my sites. So it gives me 0 if I have 0 fermions and 0 if I have 2 fermions. And so once I apply this to any generic wave function, it's going to leave me with a wave function where my constraint is actually enforced on every single site. This is what we're going to do tomorrow. Yes?
What do you mean by large
N
n?
is the number of spin components, essentially. Yeah, so you go from SU2 to SUN or SPN. Yeah, thank you. Yes?
So do you worry about the self-consistency of the
So you can, certainly you can, but I guess what I'm trying to get across is you could solve this mean field theory and say this is the solution of the mean field theory. But that is not going to satisfy this constraint on average. And so it's not going to really be a very good solution. So it can tell you something, but the specific mean field solution is not something I would necessarily believe. Once you go and Gutzwiller project it and find the energy, like we're going to do tomorrow, I would believe it more. And what we're trying to learn here is just a sense of what is possible. So this is telling you what's out there. It's not telling you what the ground state is. But you do, I mean, you could solve the self-consistency condition. We're going to just find what can be non-zero. Yes?
I think this is a related question. Even if I don't worry about the constraint,
Mm-hmm.
do I get the chi-ij and delta-ij self-consistently?
Yes, so those come, I mean, so here you have this this is what's going to give you your self-consistency equation. So if you find the free energy from this Hamiltonian, you're going to have some set of equations that look like this. You're also going to have dfd lambda equals 0. This will depend on how many mean field parameters. And this is how you would solve it. It's a saddle point approximation. I've totally skipped all of the details. Does that help? Other questions? OK. So the Gutzwiller projection is one way of fixing sort of what we're missing. And let's see. So this is actually going to address this a little bit more. So once you get your wave functions, these are really going to depend on your set of mean field parameters. But these are now going to be good wave functions that are satisfying the constraint. And so you can take these and find the energy, which will also depend on your various sets of mean field parameters. And then you can minimize this energy with respect to these. And so essentially, this energy is a variational energy with some set of variational parameters. So I've used this whole mean field construction to construct these kinds of variational wave functions, which I can then evaluate their energies and see how well they work. And it turns out they work pretty OK if I actually should have a spin liquid there. And this is the whole idea behind variational Monte Carlo. And Hitesh is going to talk about that a little bit tomorrow before you guys actually run the program. OK, so that's one thing we missed. There's another big thing that we missed, which is that there's a gauge symmetry that I didn't tell you about. So so if we take our original Hamiltonian, which I have since erased, and I write my spins using this parton representation, this has a hidden SU2 symmetry. So there's a real SU2 symmetry, which is the spin symmetry. But there is also essentially an extra SU2 gauge symmetry. And so the easiest way to see this is if I take F alpha, I can perform a continuous particle-hole transformation on it. And I'll see that my Hamiltonian is totally invariant under this particle-hole transformation. So it's kind of like an isospin SU2 gauge symmetry. These are particles that don't have a real charge, so it's really a gauge symmetry. And you can see that since this is mixing particles and holes, this is going to mix chi and delta together. And that's why I said, you have your chi, which looks like a hopping, and your delta, which looks like pairing, but actually you can't really tell which is which. And really, pairing and hopping are not sort of uniquely defined here. You can map one to the other. But when I write down any sort of generic mean field ansatz, this will typically break my SU2 gauge invariance. And I can do so in two ways. I can either break it down, instead of SU2, have a U1 gauge symmetry. So this is like the typical charge conjugation, still I, U1 symmetry. But now there's no real charge, it's just a gauge charge. Or I can break this down further and have just a Z1 symmetry, or Z2 symmetry, sorry. Where I can just change the sign of the fermion on with some given pattern. And this is always going to be a symmetry of my Hamiltonian in some shape. And so when I look at the low energy excitations, I have to consider both my spin-ons and also some kind of gauge boson associated with my leftover gauge degrees of freedom. So you would do a Bogel-Yubov transformation to diagonalize this Hamiltonian. So this is, right, so kind of. It's a different group. So Bogel-Yubov transformation, well, it looks like a Bogel-Yubov transformation for bosons. Right, so for Bogel-Yubov transformations, there's Koch and Cinch. So that's an SL2 group, and this is SU2. Yes?
Sorry, real quick, should that be SU3 gauge symmetry, that second?
No, it's SU2, SU2 gauge. So I only have two types of, so actually you can see it best, so like if you write it like this is a two-component spinner, it's a Nambu spinner, and this is actually, I can write this as inserting essentially some kind of SU2 matrix acting on this. This would be actually Uj, because that depends on J, and Ui dagger. So, Okay? Essentially, there's two charge components. All right, so our low energy excitations are generically going to be spin-ons and gauge bosons. And these will be either U1 gauge bosons or Z2 gauge bosons, or in some case where you don't break it, they could be SE2 gauge bosons. Yes?
So you get those from Goldstone, right?
They're not from Goldstone, no. There is no symmetry breaking here, so there are no Goldstone modes. The easiest way you can see, all right, so remember this is my U1 gauge transformation. So I'm going to take, the way you see your gauge bosons is they don't show up at mean field level. So your spin-ons show up at the mean field level. And your gauge bosons show up when you try to say, okay, maybe my mean field is not the best thing. Let's look at some corrections to mean field theory. So you can take your chi ij and write it as, so this is your real chi ij, and you can write it as some kind of mean field term. Plus some kind of amplitude correction. Times some kind of phase fluctuations. So I'm assuming that my mean field chi was real, and you can define this how you like. But if you plug this in to your Hamiltonian here, go through and calculate your corrections to your free energy, or your corrections to your action, you will find that what pops out is going to be your mean field term plus a gauge term. And I'm not going to derive that. It's kind of tedious. Please look at the review by Savary and Valence, or the review by Lee, Nagos, and Wen is actually probably a better place to see exactly how you derive this. But essentially, this is where it comes from. And this is going to turn into your gauge field. Okay. So once you work through this, what you would find, let's see. So I'm going to give a very gross oversimplification. And then I'll tell you how I'm lying to you. So this is your mean field Hamiltonian, your fermions having their quadratic dispersion, or hopping on some lattice. This term looks like a Maxwell term, right? So I'm assuming a U1 gauge fluctuations. I have a Maxwell kind of energy dispersion, essentially, for my bosons, right? You can also write this as some kind of fake gauge, some kind of electric field squared plus magnetic field squared type term. The key point, this is looks just like normal QED, almost. So let me tell you where I'm lying to you. So the first thing is I've written down something continuum, and we're really on a lattice. So there's a way to write this down on a lattice. It's just not as pretty and not as recognizable. So you can write down a lattice gauge theory. The other thing is that if I take A to A plus 2 pi, I should get back all of the same physics because it only shows up in this exponential here. And so this is actually a compact U1, which is essentially the U1 group defined on a circle. And when you do electromagnetic gauge theories, this is U1 defined essentially on a line. so it doesn't loop back on itself. Okay, so these affect essentially computations, and this one does affect some of the physics in a way that I will tell you. Yes?
So this parameter G,
Yes.
its value will be decided by what?
It will depend on your mean field fermion term. There's just some constant out there. And it will not be large, or actually, sorry, this is just, there will also be a coupling of your fermions to your gauge field here. It will come in like the usual kind of Peierls coupling. And the coupling between the gauge bosons and your spin-ons is not weak, so you actually have to really consider it. Okay, so, like 15 minutes left, okay. So what we have, to take a step back, we have spin-ons and we have some kind of gauge bosons, and we have to consider both of these when we're looking at our low energy degrees of freedom. And we're really only interested in low energy degrees of freedom because that's where we expect the physics to be kind of universal. So this was, of course, one option where I have U1 gauge bosons, and this is not the only option. Z2 was another option, and then there's a third option, which we haven't covered yet. Let's leave that here. Okay. Okay, so we can have U1, which is this symmetry here. We can break this U1 down to Z2. In this case, you're going to get a Z2 lattice gauge theory, and this turns out to, your gauge bosons are gapped. And essentially what happens here is the exact same thing that happens in a superconductor, where you break your U1 gauge symmetry and your photon becomes massless. So here, you're going to have a gapless photon. Here, you're not going to have a gapless photon. You can say that it's been Higgsed. So this is also known as the Higgs phase. Right, so we've gapped out our gauge boson, so now we don't need to worry that we can eventually go low enough in energy that we don't have any low energy gauge bosons and we just have low energy spin-ons. Okay, the other option is that in addition to my Maxwell term, I can get a Chern-Simons electromagnetic term. This only works in 2 dimensions. This also gaps out the gauge bosons and essentially turns my system into a quantum Hall state. This dominates your Maxwell term, and this is what you have when you have chiral spin liquids. Okay, so these are sort of all of the possibilities, right? I have my spin-on Fermi surface, my Dirac cones, my band or Chern insulators. This one is connected to the Chern insulators. These guys can have any of those things in this sort of mean field picture. And so what I can do from here is rely on a lot of heavy-duty quantum field theory work that other people have done that I'm definitely not going to go through that tells me what I can expect for stability. So essentially, here, my gauge bosons are gapped, so everything should be fine. If I go to low enough energies, everything is stable. Here, my gauge bosons are not gapped, and so I really have to worry about what the effect of the matter to gauge boson coupling is. So I'm just going to write up sort of a cheat sheet of the results here. And this is, in a sense, all of the kinds of spin liquids that are possible, that at least within this picture. Okay, so all right, so the first thing I want to look at is my spin-ons. So these can either be gapped, in which case then I want to go on and look at my gauge bosons. So let's do this. So if I have U1 symmetry, then if I'm in D equals 2, this is totally unstable. Essentially, you can have defects in your gauge fields that proliferate and take you to a totally different phase. In D equals 3, this is actually stable. This is essentially quantum electrodynamics in 3 dimensions. It's called the Coulomb phase. It has a low energy gapless photon and is found in some theories of quantum spin ice and potentially experimentally. Okay, so that's for U1. If I have Z2, gauge symmetry and gapped spin-ons, then I have a gapped state. I have no energy excitations. This is topological. I'll have topologically degenerate ground states. I can calculate my topological entanglement entropy. It's log 2. I have no gapless edge states. And examples of this are toric code, it's unclear if it is or is not valid on the Kagame, but this is typically what is referred to as a Z2 spin liquid. Okay. All right. And then the next option is if I have that Chern-Simons term, then this only makes sense in D equals 2. And this gives me a chiral spin liquid. Which is, again, gapped, topological, has degenerate ground states. It also breaks time reversal. And you have anions. So your low energy excitations, your spin-ons are actually generically not fermions, but anions with 1/m statistics. And so the sort of simplest example, you have m equals 2, and then you have semionic spin-ons. And I'll talk in a minute about how you can actually get these from this fermionic picture. And you end up with m chiral edge modes. Okay, so this is for gapped. So do gapless over here. Okay. So if I have gapless spin-ons, there's 2 types that I can have. Well, there's more than 2 types. But typically we'll look at Dirac fermions, so they look basically like graphene, or I have a spin-on Fermi surface. So if I take either of these and I have a Z2 symmetry and Z2 gauge bosons, these are totally stable. And so these can describe basically gapless spin liquids with some kind of Z2 spin liquid, or Z2 gauge symmetry, and the gauge bosons are gapped out. If I have U1 gauge symmetry, then It is a little bit more difficult. And basically, Dirac spin-ons. So the answer is not totally clear, but Dirac spin-ons are definitely unstable in 3D, and likely stable in 2 dimensions, but they're going to be strongly coupled. This is something called the algebraic spin liquid. Because if you calculate the spin correlation function, you're going to get algebraic correlations, and then a spin-on Fermi surface with a UN gauge symmetry is also thought to be stable. Okay. And this has been predicted on the triangular lattice with ring exchange. But none of these things are particularly clear. So this is a sense of what's out there. Is that kind of clear? Any questions about this? And we have, okay. So reach the end. I'm going to use a little bit of the beginning of our tutorial to actually tell you about projective symmetry groups, because I think everyone wants to eat dinner. And so that will take you through a little bit of the more concrete things, which you'll end up basically saying how to take this and know what you actually have. Yes?
So like in Heisenberg chain, you also have like gaplets between this square and side.
In, sorry?
Heisenberg chain.
Oh, yeah. So I'm only talking about d equals 2. So, I mean, yes, in 1 dimension, everything, you don't have magnetic order, and you can have gaplets, you can have spin-ons, certainly, and this is very well understood. It's not a kind of topological order in the same way here. Yeah. Other questions? Or, I mean, you're going to say the same thing.
Yeah. Well, are there other questions? And then we can probably wind down.
All right. Yes. Right. So, okay. So quantum spin ice is a type of spin liquid. So spin ice is a particular pyroliquor lattice where you have some kind of, it's actually a classical spin ice is the thing that's been most well studied. But you can have essentially the same Hamiltonian. It's on a pyroliquor lattice with Ising local moments, and this is thought to be quantum spin ice. It's a type of spin liquid, yes. Or really a type of Hamiltonian. Is that, yes, Nandini? So you can, oh, no, I mean, it's, well, I mean, I have, if I just imagine electrons on forming a Fermi surface, those are going to have a, right. So, okay, so I wouldn't calculate it in the mean field, but you can calculate it using variational Monte Carlo and find the topological. I don't know for sure. I suspect that the enforcing the Gutzwiller projection is probably extremely important. I don't think you would get the correct quantized topological entanglement. Yeah. Then, right. Yes. Yes. Yeah, I agree. That's a good point. Yeah.
One last question.
Is there an advantage of using this fermionic mapping rather than, let's say, Holstein Primitkov or some other form?
Oh, well, Holstein Primitkov is great if you're wanting to look at something near a particular magnetic order. Here, I actually really don't want to look at magnetic order at all, so I've chosen to use fermions, and I can't I can't look at magnetic order. If I chose to use bosons and just replace all your F's with B's, then I can see magnetic order showing up for that, but it's really just a good tool at looking at where you don't have magnetic order.
Okay, great. Thanks, Rebecca.